Good afternoon, everyone, to this fourth and final set of PSYCHE guest lectures, for which we have two different speakers on today's program. Before we start, I would like to stress the following good practices. Please turn off all your cell phones, put your microphone on mute, and use the chat function for communication and questions. Our first speaker today is Benoît Corteuzer from CERTECH. Benoît graduated as a chemical engineer from the University of Louvain-la-Neuve and obtained a PhD in chemistry, more specifically catalysis, at the University of Limerick in Ireland. Since 1996, he works at CERTECH with focus on inorganic chemistry. He was involved in the treatment of styrene by catalysis oxidation, the development of hydrophobic coatings, and air treatments by photocatalysis. For the latter, he was a Belgian expert at the CEN-TC 386 photocatalysis committee. Benoît, welcome, and I give the word now to you.
Hello, everybody. Good afternoon. My name is Benoît Corteuzer, and as say Elisabeth, I'm working in CERTECH for quite a long time, and more precisely in the intensification of process. And for that, I'm also responsible for the PSYCHE at CERTECH. Then today I will show you, speak about syngas purification, give some example of what is already done in industry, and also how at CERTECH we carry out some experiments to find a new way or new materials to treat the syngas.
Yes. Wait.
Ça ne change pas. Okay. The syngas actually is an abbreviation of synthesis gas, and is a mixture which is comprising mainly carbon monoxide and hydrogen, with also some traces of CO2, water, and other little low alkanes. And it comes from a different materials that can be just coal, some oil, some biomass, but also some plastic waste. And it can be produced also by different processes, such as steam reforming or partial oxidation or gasification. And all of those different processes will give a different type of syngases. And the use of the syngas can be different ways, like production of hydrogen. We can do some synthetic fuels with the Fischer-Tropsch synthesis way, or produce methanol and other compounds. Like I said, the composition of the syngas will depend on the starting raw materials and the process used. And usually the composition is mainly hydrogen, carbon monoxide, carbon dioxide, some water in those range, and also some low alkanes. But beside all of those compounds, there is also some impurities. And that could be a problem for the use of the syngas afterwards. Use syngas here is just a picture of where the syngas is used. Most of the production is for the production of ammonia, and then production of hydrogen, so methanol, but also through the Fischer-Tropsch process, it can be transformed to a liquid, and that can be started to make some synthetic fuel. And it's in that way that the project PSYCHE is in it, and the project is Interreg program funding, and it's collaboration different universities, the Ghent, UC Louvain, Ecole, Nationale Supérieure de Chimie de Lille, CNRS, and CERTECH. And the project is that to use plastic waste, to treat them, to do some gasification, and after the gasification need to have some purification to be able to use the syngas in the Fischer-Tropsch synthesis. That could give us then in the end some olefins. But to be able to work in with the syngas that we can get from the plastic waste, it is very important to analyze perfectly the gases and to know all of the impurities that can be found on the flow. And also it's important to know what level of those pollutants can be on the flux for working for the Fischer-Tropsch, because some of those pollutants, like sulfur compounds, can poison the catalyst used for the Fischer-Tropsch system synthesis. Then it's why it's very important to analyzing all of the gases produced by the gasification of the plastic waste. This is some example of contaminants, some particles, which can be silicates, some ash, with concentration quite heavy, around 1%. Some acid compounds like chloric acid or sulfur compounds like H2S and COS, which quite very often to found on the syngas. We can have some ammonia or organic compounds like benzene and dioxinotares. And we can see the concentration of those pollutants can be quite low, around 10 microgram up to a few percent. But as we can see here for the Fischer-Tropsch synthesis, the concentration of those pollutants has to be very, very low, and some have to be totally removed. That is why it's very important to know and to characterize well the syngas flux. For the synthesis of the syngas, to be able to clean it, to remove it, there are actually two main ways. The first one, which is called the cold gas cleaning process, so GC, is actually something which is quite well known, and that there are a lot of literature and publication on it. The major problems with the cold gas cleaning, like it's called, is that we need to cool down actually the gas produced during the gasification, and means that there we can lose a lot of energy, and also a lot of the system used can give some byproducts that needs to be treated, like some use water or solvent and so on that needs to have for the processes. The second way is called the hot gas cleaning process, and actually there we do not need to cool down too much, or sometimes don't need to cool down at all the syngas flux. It can work at higher temperature. It's possible to have some sorbent that can be regenerated, and usually we should have a less byproduct to be treated by that way. And there is some elements like heat exchange that we do not need to have anymore. The major problems for this way is that it's not as well established as the cold gas cleaning systems, and still need some development to have something at industrial scale. This is just a quick comparison between the two ways of cleaning the syngas, and the different type of techniques that we could find to remove some impurities. Like for solid particles, ash, there is a filtration at low temperature, some cyclone or scrubber with some solvents. For the hot gas cleaning, it's also filtration, but working at higher temperature, then we need special materials like ceramics or metallic candles that can work at high temperature. For the sulfur compounds, usually mainly H2S, COS, there are different possibilities on the wet process, adsorption in amine or methanol or different type of solvents. We could use also some adsorption on activated carbon, modified activated carbon. Usually for COS, we go through a step which is a hydrolysis step actually to transform the COS on H2S, because the COS is quite difficult to remove. And often there is quite a lot of waste to be treated after the cleaning units. For the hot gas cleaning, it's possible to work with some methyl oxide sorbent, which will react with the sulfur to produce a sulfur, but it's possible to regenerate the sorbent, which is quite good. For the hydrogen halides, usually it's a neutralization in both cases. Can be either wet or dry systems, and there also this means we're producing some waste. Methyl carbonyl that we could find on the flue. There it's usually catalytic decomposition, then to get the oxide of the metals and CO2 in the end. When we have some nitrogen compounds, usually it's Denox processes, which is quite well known and used. Heavy metal like mercury, for example, usually we need to have a condensation, then cool down the flow, and there's adsorption in activated carbon, or sometimes reaction with a copper oxide solid. A hot gas cleaning system is more or less the same, but it's possible also to work with the copper oxide at higher temperature, and there is also possible to have a regeneration of the copper oxide on that systems. Finally, for tars, means benzene or other heavier organics, there is usually a cracking system that we're working, or doing a condensation, that means the cooling down to be able to capture all of the pollutants present. I will just pass through a few examples of what is available in the industry. For example, like in this way, we have a cyclone filter. The flux go through this way, and there is a centrifugal system which can separate the particles. Here we will find particles there, and here is a clean gas. It works well, but not too much for very fine particles, less than 5 to 10 microns. It's not very effective. It's better to use then those type of filter, pocket filter. They're quite very effective, but you could not work at a high temperature with it. Or then you have those metallic candle here, which is actually more or less the same as a pocket filter. The only difference is that all of those candles are just in metals. That is for particles removal. Also, you could have some scrubbing. Then just washing with some liquid or water, then we can trap some particles in that way. This is a summary of what we could find in the literature and industrial ways to remove the acid gas, and mainly for sulfur compounds. Actually, the 3 types of solvent used. One they call chemical solvents. That means there is a reaction between the amine and the sulfur pollutants. It's possible in some cases to get the regeneration of the solvents by heating the system. Then we could recover the solvent and start again the work. The second system is physical solvent. Actually, there is working with heavier solvent, or there is a good interaction between the liquid and the sulfur. It's very used when you have a very high concentration of pollutants and working at a low temperature. And it's also possible to regenerate it, but you need to reduce the pressure. And in reducing the pressure, you get a separation between the adsorbed sulfur and the solvent. Then you can recover the solvent. And the third one is the mixture of both. Then he tries to get the best of the chemical solvents and the physical solvent on only one system. And also it could be regenerated. And in some cases you can remove HOS, CO2 also, or COS, but also some hydrocarbons, some ammonia. Then you could be interesting depending on what type of pollutants you need to remove. The hydrogen halides system, actually it's these two ways. Could be just a scrubber, or you could actually introduce the calcium hydroxide, for example, as a powder in the flow of the gas. Here there is actually a reactor where you introducing the particles. It comes in contact with the gas to be clean, and then in the end here you have a particle filter to actually to separate the particles and the salt obtained by the reaction and the gas. Then here is the clean gas of the exit, and here you just recover the powder. Again, you're producing some salt that has to be treated. For tars removal, if you are not working at a high temperature that is burning it, you can do a condensation, and this actually a heat exchanger where you have in somewhere the fluid that you want to treat, and you have a liquid here. Often it could be the water. You have a liquid that will just reduce the temperature of the gas, and there we have a concentration of the tar, because the boil point is around 100 and 300 degrees, and you can have then a liquid. Also, because you will have some liquid, it's possible to capture some acid or even ammonia in the solvent that you will get there. And the exchange of the heat between the gas and the water can be recovered. Finally, another way to remove compounds could be an adsorption technique. Often what is used is activated carbon. Now the temperature is quite limited, working at often at a room temperature or maybe up to 200 degrees. And there we are just the flow passing over the activated carbon. There is an adsorption here in the porosity of the activated carbon, like we can see here. And you do have a clean gas in the exit. Sometimes it's possible to have a regeneration of the activated carbon, and for that we just passing a clean gas through the regeneration, heating up, and normally if we can remove, we get here the exhaust gas with the pollutant which was concentrated in the activated carbon. But most of the time, those adsorbents are just a waste and has to be treated in the end. Then it's used for many types of compounds, for COV, for example, but also for sulfur compounds, for heavy metal compounds, and so on. Now I will just show you how we can test it at laboratory scale and how we can do it quite easily, study the availability of new materials or new solution to capture some pollutants. Then it's quite simple. We do have here a cylinder with the gas composition to be representative of which type of pollutants we want to remove. Often we try to make a very simple mixture at the beginning, just to study one or two pollutants at once. We can dilute it with some dried air, also nitrogen or the gases, and it's possible to adapt the humidity. Then it's also possible to study the influence of humidity on the performance of the system we want to characterize. We have a treatment devices, which is often placed in an oven. This permits to control quite well the temperature, because temperature is very important parameters once we want to do some adsorption study. But there is also what we call a bypass here, and is connected to an analyzer. The analyzer can be a GC or GCMS or just mass spectrometer. Could be also only if we're working in a liquid or in water, you can just follow the pH of the solution. That could be the analyzer. The bypass actually is quite important, because it's the way to stabilize the flow and to have the starting concentration of the pollutants you want to look at. And here is on the graph, you can see this is my starting concentration of the two systems. Once the flow is stable, we can change the valve, and going through the treatment devices here, it's what is observed here. Then at the beginning we have nothing, because in the device you have no pollutants, and then just either coming quite rapidly to the starting concentration, or it can stay quite a long time before to be detected in the outlet of the reactor. In these cases, for example, there's about 30 minutes before to see the H2S. This is what we call the breakthrough time, and this is very important parameters to be able to sizing some removal process. An example of bottle here with some solvent. We fill up the bottle with some glass beads, which permitted to have a long contact time of the pollutant, which is coming from here, the inlet, passing by the bottom, coming back and going the outlet, and the outlet is connected to the detector, and then we can follow the adsorption of the solution of the pollutant in the solution. This is a wet process. Can be a water-based systems, or can be just a solvent, organic solvent systems. Or we can test also on a similar way what we call dry process. Like here, it's a picture of activated carbon, actually modified to be active for the removal of sulfur compounds. The same, we fill up a reactor with those pellets, put in the oven, and we just follow the absorption of the pollutant by the activated carbons. I will just show you a few examples of results of different types of solution we tested. This is one of the first tests was only a neutralization reaction between H2S, COS, and the ammonia solution. The first we can see is that this system is not effective at all for the COS. Then you can see very quickly come back to the starting concentration in this way. It's more effective for H2S. We can see it takes about 30 minutes before to detect the H2S on the exit of the outlet of the reactor. Another test was testing one type of activated carbon called CH3 from Chemviron. This carbon was modified especially to be able to be active to remove some sulfur compounds. And we can see on the curve that even COS and H2S can be removed by the activated carbon, but COS takes quicker timeless time to be detected in the exit of the outlet of the reactor. And we're working at 3 different temperatures, 30 degrees, 150 and 200 degrees. And what we observe is that for H2S, there's more or less no difference on the breakthrough time, but there's some increase on the COS. That means the temperature, increasing temperature from 30 to 150 degrees has a positive effect on the COS removal. Then with the starting concentration and the time here to pass through, it's possible to sizing an industrial process using this type of activated carbons. Once we detect the pollutants, usually we say on 5% of the inlet concentration, you need to change your activated carbons. Also, these carbons, we tried to see if it was possible to regenerate it, the activated carbon, just by heating up the activated carbon on the nitrogen, and see if we can detect some H2S or COS in the outlet of the reactor. But actually, we did not see any sulfur production. That means this activated carbon could not be regenerated to be able to reuse it in future cleaning systems. Activated carbon is also well known to remove some VOC. Then you have at CERTECH a cylinder with a mixture of 4 pollutants, which are acetaldehyde, acetone, toluene, heptane. And those were used to characterize the ability of the activated carbon to remove them. And after 70 hours, we did not see any VOC in the outlet, but the cylinder was empty. Then we could not go further to characterize the uptake of the activated carbon on VOC in this concentration. Also, what is very important when we have working with syngas is not only sulfur impurities, but you could have other things. Then the best is try to have a mixture with more than 1 or 2 pollutants. It's why here we do have a system with benzene and toluene, which actually benzene toluene can be tars. And we just use a small amount of activated carbon, just not to have run too long, for the removal of that mixture. And we can see that toluene, which are at low ppm, on 120 ppm, it's totally removed from the gas phase. Benzene is removed, but after about 30 minutes start to be detected in the outlet of the reactor. And H2S and COS are very low activity in comparison of the VOC. There are many phenomena which could happen in these cases. Usually an absorption is very effective when the concentration of the pollutant is high. Then we could expect that benzene should be more effectively removed in comparison to toluene, because toluene is a very low concentration. But in this case, toluene actually is very well trapped by the COV. That means there is a very good affinity with the adsorption sites on the activated carbon. Also, because there is a mixture and there is only one, maybe two types of adsorption sites, if these different types of affinity of pollutants with the adsorption sites, you have a competition between the pollutants. And this indicates that the toluene is very good affinity, much higher than for the sulfur compounds and the benzene compounds. Also, we can see if you want to use this activated carbon to clean up this type of mixture, the activity will be very low, because you will need to change it to remove due to the low activity on COS. It's why it's very important to characterize very well all of the different processes, and not only with one pollutants, but with a mixture of pollutants. Finally, we try to work with two solution, amine solution, which normally are very effective to remove the sulfur compounds. We can see that the first one, the ethanolamine, 50% in water, we do remove some H2S for about 20 hours. But COS, actually, we have about 2/3 of the COS can be capped, but not more. And with the diethylanolamine, there we have quite a good uptake for H2S, and again here it's about 50% only of the COS which is capped by the solution. And we can see that the diethylanolamine is much effective for the removal of H2S, but it's not enough for the COS. That is why to make a dimensionment of it, it's very important. Either to change, that means to have a first step that you will modify the COS to produce a H2S and CO2, and then the H2S can be removed by this type of solutions. This is some example of the dry, the cold dry system, cleaning system, and now I'm just presenting you some development on the removal of sulfur compounds, but at a higher temperature. Then Kobayashi shows that it's possible to remove some sulfur compounds on zinc-fed systems, and to regenerate it, the zinc ferrite, to be able to reuse the sorbent. Then very simple flow sheets here. You have the syngas, which has to be clean. In these cases, it just has a halide removal unit. And then there's a 3 reactor, which are using on the first step that will be to cap the sulfur in this way. Once it's saturated, the system will be actually regenerated in a second reactor by some oxygen, and then that will produce some SO2, which can be capped in another way to use the CO2 and to produce some sulfur. And the third one is the reduction of the system before starting the cycle. Then this is a cycle. There is a reduction step. Then you have the absorption of the sulfur compounds. There is some regeneration with air, producing SO2 that can be used in other processes. And then after regeneration, we start again the cycles. At CERTECH, we did some synthesis of a zinc ferrite system by what is called auto-combustion techniques. Then we're using some nitrates precursor in water. We had some citric acid, and then we're changing the pH to get a pH neutral. Then we leave the mixture in the oven at 120 degrees to have a gel. The gel will dry, and once it's dry, we're just heating up to 250 degrees, and we can see like a cake which is formed, and then it's just expansion of the gel, and then we have a very thin powder of the zinc ferrite. Then we just characterize with the DRX spectrometer to see if we got the right phases, and we saw in blue that's our compounds, and the dot points are the points for the zinc ferrite diffraction peaks. That means we got the zinc ferrite as expected. In the same way, we modified and with some copper or some nickel with the zinc ferrite, maybe to increase the activity of the systems, because copper oxide or nickel oxide can also react with the sulfur and have ability to remove some sulfur compounds. Then we have this unit to test the ferrite systems. Here we have a small reactor. We're working with a few milligrams of the ferrite, around 50 milligrams of the ferrite in the tube. We have on the inlet one way for the air, one way for the hydrogen for the reduction, and one way for the mixture of sulfur or the type of pollutant we want to look at. And of course, we can make a bypass to study to have the right inlet concentration. The first protocol we just used the powder like we prepare at 250 degrees because we saw with the zinc ferrite that we got the right phases. Then we just did a reduction at 450 for 1 hour. Then we did the sulfur removal step at 400 degrees and a regeneration in the air at 450 degrees. This is an example of 4 runs obtained with the zinc ferrite oxide, zinc ferrite, for the absorption capacity for H2S and COS. This curve in blue is the first test, and in dot line is for COS on the first step. The starting concentration for the H2S was 500, and for COS it was only 50 ppm. Why did we change this? Is just because on the literature we saw that the COS concentration usually is about a tenth of the H2S concentration. Then it's to be more realistic that we modified our mixture in comparison of the first experiments I showed you just before. Then we have good activity for both COS and H2S on the first round. And if we do a calculation, we got actually a capacity of, for H2S, of 7 millimoles per grams of solids, which is almost the theoretical value that we could have with that type of solids. Once we making a second one, we can see there's a decrease on the breakthrough time for H2S, and the third and fourth, we still have a decrease, but then on the fourth it's more or less the same as the third. And here it's the curve on blue, and we can see there's a decrease for the two first runs and then start to stabilize. But for COS it's totally different. Actually, on the second run, we do not have uptake of COS, but we have a production of COS, which is quite a bit strange because we did not expect it to have those type of behavior of solids. And then later on, I will explain why we do have this type of production. But first, we wanted to know what happens between the first, second, third runs, and see if our regeneration protocol works well. Means that we made some DRX analysis of the zinc ferrite systems at different steps. On the first initial products, we do have the zinc ferrite, but also some trace of oxide, iron oxide. After the sulfidation test, we do have what is expected, some sulfur, iron sulfur and zinc sulfur, which what is expected to have. And after the reduction, actually we found some zinc ferrite, but some zinc oxide, iron oxide, and even a small peaks of iron metals. But with the DRX, we did not see any sulfur after the reduction processes. Then we thought that the temperature 450 was good. But if we did some observation on microscopy, electron microscopy, with a EDX analyzer, and in the EDX analyzer, actually some sulfur is detected. That means maybe that 450 degrees not enough for the regeneration of the sulfur systems. But first, we wanted to know why we do have production of COS, and we were very surprised after the reaction, because between all of the tests, we do not open the oven. That means we could not see the inlet of the reactor because it's in the oven. But when we open it, we observe this solid in the inlet of the reactor, and before the zinc ferrite powder. And we did some DRX analysis, also some microscopy analysis, observation with DX analysis, and we were surprised to see that actually that solid, it's nickel sulfur, two types of nickel sulfur. But that means that happens before the catalyst. That means it's a reaction which was made before the entrance of the inlet of the reactors. Then we tested two different mixture, and actually our pressure regulator is a nickel coated brass pressure regulator. And if we do a reaction with empty reactor just with a mixture of COS, H2S in nitrogen, in the inlet we have nothing, but in the outlet we have some traces of sulfur. And if we do the same with the mixture with the CO2, we have in the inlet that black metallic solids. And actually, looking in the literature, we found that at low temperature, we could have some reaction between the nickel and the carbon monoxide at low temperature to form nickel tetracarbonyl. And those nickel tetracarbonyl actually are very, very toxic, but it decomposes above 150 degrees. That means the nickel carbonyl, we got it in the flow at room temperature, I'll say, is decomposed in the entrance to produce nickel, metallic nickel, and CO. And this nickel reacts actually with the H2S, which is present in the mixture to form some sulfur nickels. And that is what we observe here. Also, nickel sulfur actually catalyze the reaction between CO2 or CO and H2S to produce COS, which explains actually why on the second test we got some production of COS and not uptake of COS. That actually is a side reaction due to the presence of this nickel sulfide in the inlet of the reactors, and that's quite inconvenience because we could not study perfectly the activity of our solids due to this presence of this sulfur, which give us a side reaction which was not expected. Then we decided to order a new mixture without carbon monoxide to be sure that we do not have that production of nickel sulfide in the inlet. We carried out a test with the empty reactor, and of course, no COS productions. We did not see any sulfur nickels in the inlet as suspected. And then it means we could study in the real activity of our systems for the removal of H2S and COS. Also, I just explained before that on the microscope analysis of the regeneration products, we still observe some sulfur. And then for that, we decided to study the regeneration step by making what's called a TPO. That means in temperature program oxidation of the solids. We just actually pass through the sulfur zinc ferrite reactor by increasing the temperature very slowly from room temperature up to 600 degrees. What we observe that nothing up to 120 degrees, then they start to have increase of SO2 production, a decrease, a second peak, probably because we have the zinc sulfide and the iron sulfide, and probably two types of sulfide, maybe three types of sulfide, depends, which could explain those two peaks. And the first protocol, we did the regeneration at 450 degrees. That means that temperature we were not able to remove all of the sulfur presence on the solids. And up to 600 degrees, we still have presence of sulfur. Then we decided to modify our protocol by working at 600 degrees for the oxidation, and we started the protocol by starting calcination of all of the solid at 600 degrees. Then we are be sure that the first step, the catalyst, will be on the same condition as the second and third one, because the temperature between 250 and 600 degrees, there's quite a big difference in temperature that can modify the structure of the solids, the zinc ferrite. Then the second step is the reduction at 450. We did not change that. The removal at 400 degrees, and start again the regeneration step at 600 in the TPO mode. That means we could register it all the time at the SO2 productions. We did the new protocol with the 3 different solids, the copper modified zinc ferrite, calcine at 600 degrees. And we saw that actually the first run here in blue, we have quite a good activity on H2S and COS. That the initial concentration activity is of 7 millimoles per grams, which is equivalent of the 2 other solids. And we have a decrease with the second, and surprisingly increase again. Then this is to be look at it more deeply. But in these cases, you can see that there is uptake of the COS and no more production of COS. Why the first test we carried out with copper zinc ferrite, we did not have a good activity. Actually, when we did some DRX measurement on the fresh copper zinc ferrite at 250 degrees, that system was amorphous and no crystalline. That means we did not get the right phases, and that probably explains why it was not active as the other ones. Because at 600 degrees, if we do a DRX system, we do have a crystallized particles. The test with the nickel zinc ferrite, it's a bit different too. Its activity on H2S is quite interesting. Okay, we lost something here in the third regeneration step, but surprisingly, that the second, third, and fourth test we have production of COS, which was not expected either. But probably what's happened is that the 600 degree maybe is not enough for the nickel zinc ferrite modified system to be able to regenerate it completely, the nickel zinc system, and probably we still have some nickel sulfide presence. And we know that the nickel sulfide catalyzes the reaction of COS with H2S and CO2. That explains why we do have this strange behavior there. Finally, the zinc ferrite itself, we did three runs here, and you can see the initial capacity 7, like usually, and slightly decreased, but the third one we have still 6 millimole per grams. That means it keeps good activity, and for COS also we have quite a stable activity. This explains that the zinc ferrite could be a very good system to remove sulfur compounds, and either both COS and H2S, and we'll be able to regenerate it, and that means we can have cycles with always the same solids for the removal of COS and H2S at high temperature. To conclude my presentation is just that syngas composition actually depends deeply on the source of the raw material used, which is charcoal, biomass, plastic waste, oils, and so on. The necessity to have a cleaning process and the types of the process will depend also on the use of the syngas in the end, because all of the final use doesn't need to have the same quality on the syngas composition. Probably the more stricter system is for the Fischer-Tropsch processes, which needs to have very, very clean syngas systems. Also, the cleaning system of syngas will depend on which types of pollutants needs to be removed. That means we really need to have a very, very deep characterization of the gases to choose the right processes and to be sure we did not forget some pollutants. Most of them are particles, sulfur compounds, nitrogen compounds, tars, heavy metals, maybe some hydrogen halides and metal carbonyls. Probably could have still other types with plastic. Depends of what type of plastic is used and which type of what is inside the plastic itself, and then that could influence the pollutants be present in the syngas. And as represented also, there is different ways to clean it, the syngas, either the cold gas cleaning, which is very established syngas, but could have some drawback by some ways to be treated in the end, or the hot gas cleaning process, which is the advantage that we do not need to cool down the flow. Is quite important for the Fischer-Tropsch because there is at high temperature, then we do not have that step to cool down and to heat up against the syngas if we can work at hot gas cleaning. And we show that there is some solids which could give a good activities for the sulfur systems. It means also because there are lots of different types of pollutants that the syngas process, cleaning process is very complicated and needs more units than only one unit can do everything together. Okay. And just a knowledge for the Interreg and all of the financial and colleagues. Okay, thanks a lot for your attentions.
Thank you, Benoit, for your interesting presentation. Our second speaker today is Professor Joris Thibaut from Ghent University. He obtained his master's degree in chemical engineering in 1998 at Ghent University, where he also continued his PhD studies on single event microkinetic modeling, SEMK, of hydrocracking and hydrogenation. In 2003, he went to the Institut de Recherche sur la Catalyse in Lyon, France, for a postdoc on high-throughput experimentation before being appointed as assistant professor in 2005 and subsequently associate professor at Ghent University. Since 2014, Joris is full professor in catalytic reaction engineering at the LCT at Ghent University. Today, he is heading the catalytic reaction engineering research group, comprising about 15 junior researchers. They actively investigate a variety of large-scale industrial reactions and, more particularly, the rational design of the corresponding catalysts, as well as of the reactors in which these catalysts are employed. Ideal gas phase reactions, as well as strongly non-ideal liquid phase reactions, are addressed. Research projects range from bilateral contracts with industry up to government-funded large-scale integrated projects. Professor Thibaut recently became coordinator of eConduct, a Horizon Europe project in the framework of electrified catalytic reactors. So Joris, now I give the word to you.
So today I will talk also about work that has been performed as part of the PSYCHE project, And in fact, a part of the work that is following up upon the cleaning, which has been discussed, the gas cleaning, which has been discussed by Benoit. So, as it is intended within the PSYCHE project, after the gas cleaning, some Fischer-Tropsch synthesis is performed, and more particularly aiming at producing light olefins. And what we have been trying to do from Ghent University within the framework of Fischer-Tropsch synthesis is to acquire a better understanding of the Fischer-Tropsch synthesis process, and do that via microkinetic modeling on the one hand, and machine learning on the other hand. And all this to assist the development of catalysts and process conditions, identifying the ideal process conditions, as is also being done experimentally by the group of Andrei Kodakov and Mirella Virginie at the Central Louvre in Lille, France. So why are we interested in modeling? Well, you see a cartoon here of the professor which is interviewing a student for his examination. And in a difficult derivation, the student has written, well, then a miracle occurs to go from the premises to the final proof he has to give. Of course, well, we do not like, or maybe we do like miracles in science, but we do not like them to leave them unexplained. We want to come up with an explanation for the miracles that are occurring. And in such complex features, in such complex phenomena, modeling can provide a good insight in what is happening. Think of a chemical reaction, a chemical reactor. You have the reactants entering the reactor, flowing through, reacting, or potentially on a catalyst, being transformed into some products. Well, in that case, a kinetic model, being illustrated here for Fischer-Tropsch synthesis, can describe how the carbon monoxide, how the hydrogen start interacting with the surface, and how the fluxes, the molar fluxes go through the reaction network. Here you see conditions which will mainly lead to methane formation. So this is more methanation than truly Fischer-Tropsch synthesis. However, that is a matter of the choice of the operating conditions. And a model can provide this insight, and from that insight, we can design better catalysts for the reaction that we are interested in, or we can even do a reactor and an entire process design. Now, for the particular case of Fischer-Tropsch synthesis, as we are interested in it from the PSYCHE project, we are particularly interested in Fischer-Tropsch synthesis for the production of lower olefins, as you can see over here. Now, Fischer-Tropsch synthesis is a quite versatile reaction. It is not limited to the synthesis of lower olefins, no, depending on the catalyst that is selected. You can also rather produce liquid fuels, or in case of copper zinc, it rather will produce methanol. Or other oxygenates can also be produced, all starting from the carbon monoxide and hydrogen mixture, synthesis gas, or in short, syngas. We have been looking at the modeling of the Fischer-Tropsch synthesis, and as part of this work within PSYCHE, we followed two different approaches. On the one hand, we followed an approach based on elementary steps, according to the single event microkinetic methodology. On the other hand, recognizing that elementary step-based modeling and detailed reactor models may become quite time-consuming, we also evaluated the use of a machine learning approach, how that could assist us to reach the same goals. So for catalyst performance optimization, our aim was to, in the end, to ultimately achieve better catalysts for Fischer-Tropsch synthesis, mainly then for light olefin production. And we did so in the first instance by employing a single event microkinetic model, a model which is based on elementary kinetics to provide more fundamental information in the reaction chemistry. That model is containing catalyst descriptors and kinetic descriptors. And particularly those catalyst descriptors are the ones which we can play with, which we can optimize in order to identify better catalysts for Fischer-Tropsch synthesis. The Fischer-Tropsch synthesis catalysts that we have focused on are iron-based ones. They are essentially low cost and exhibit an inherent selectivity to olefins, which can be enhanced by using the proper promoters, such as lead and bismuth, for example, soldering metals, as they're also called. And that was the particular focus of the even already previous work that Andrei Kodakov was leading with some work of Bengu et al. And which has been continued as part of the project with Alan, who focused on different supports and also who focused on CO2 hydrogenation rather than CO hydrogenation or Fischer-Tropsch synthesis. The reaction network is a quite complex one. You have seen a first snapshot of it already a few slides ago. Here is a more detailed representation of that reaction network, which involves reactant chemisorption and the steps indicated in red, the dissociation of CO, the water removal by consecutive hydrogenation, then also the monomer formation, so the methylene group formation, to then in the end come to chain growth, leading to higher species, which can either desorb as saturated components by hydrogenation, or which can leave as unsaturated components, and that is what we are interested in, particularly within the framework of PSYCHE. Important to also realize is that iron-based catalysts are particularly active also for the water-gas shift reaction, which makes that potential CO2, which is contained in the feedstock, that it can be employed with hydrogen to create additional CO, or vice versa, that water that would be contained and produced, that it can lead again to additional hydrogen with concomitant production of CO2. So like that, the hydrogen to carbon monoxide ratio, which is employed on these types of catalysts, can be is more variable, so the catalyst can cope with a wider range of hydrogen to CO ratios, particularly to lower ones, because the water that is produced as part of the reaction can be regenerated into hydrogen, which can then be used again for further reaction. In modeling, so theoretically, this chain growth can extend towards infinitely high carbon numbers, and that also explains why there is typically a significant wax formation during Fischer-Tropsch synthesis. In the modeling, we have considered a reaction network until 10 carbon atoms, until components with 10 carbon atoms, which allowed us to avoid end-of-chain effects, particularly and because we were working at conditions focusing on an optimal yield of light olefins. Light olefins meaning in the range C2, C3, maximum C4, So that means that the yield of components of C10 and higher was sufficiently limited. The single event microkinetic model, how does it look like? How do we work with it? Well, the single event microkinetic model essentially makes use of the reaction family concept. Within the reaction scheme on the previous slide, you have seen, or you could see, that the chain growth steps are in fact steps that are essentially the same for each and every carbon number that is considered. So whether a methylene insertion reaction, whether it occurs in a C1, C2, C3, C4 species, by employing the reaction family concept, we can assume that the energetics of those reactions are the same. And that will lead to equal activation energies for those reactions. We need to recognize, however, that differences related to symmetry of the molecules involved, that they can lead to a difference in pre-exponential factor. And that is why this ratio of symmetry numbers, of global symmetry numbers of the reactants and the transition state, why that is eliminated from the activation entropy. So that is specifically removed from the pre-exponential factor, apologies, such that the rate coefficient of an elementary step can be written as the constant single event rate coefficient within a reaction family, multiplied with the number of single events, which equals this ratio of global symmetry numbers. So, and here we have then a part of the rate coefficient which is truly unique within a reaction family, and we have the number of single events which is then to be determined during the reaction network generation. Of course, we need, when we want to calculate reaction rates, we need values for the activation entropy and the activation enthalpies, and the other numbers are essentially predetermined. Now, for the single event activation entropy, we did some a priori assessment based on assumptions related to the loss of translational degrees of freedom of the species that are involved. The activation enthalpies, according to the transition state theory, those have been determined by regression to experimental data. And that benchmark version of the model is the one that has been made, developed, and also first published by Lozano Blanco and some previous work within our lab. Important also to consider in the single event microkinetic model is that we're not just having the rate coefficients, we also need to ensure that the thermodynamics of the species that are involved, that those are okay. And for that, we have a calculation method based on the universal bond index quasi-exponential potential method, which is a method that allows us to calculate those surface thermodynamics in terms of atomic chemisorption enthalpies on the strength of adsorption of carbon, oxygen, and hydrogen as atoms on the catalyst surface. So I will not go through the detailed explanation of what is on this slide. The main point essentially is that we introduce here atomic chemisorption enthalpies, which are the parameters in the model that will allow us to relate the catalyst properties with the performance of the catalyst. So those are the parameters that will account for the impact of the catalyst properties on the simulated catalyst performance. Apart from that, there were the kinetic descriptors, the activation energies, which are considered to be invariant with respect to the catalyst. Okay. After this introduction towards the topic, I will first deal with the catalyst screening within Fischer-Tropsch synthesis that we have performed, a catalyst screening which was mainly based on using the single event microkinetic model and allowing the catalyst descriptor values, those atomic chemisorption enthalpies, allowing those to vary. That was mainly at fixed operating conditions, but of course the optimal catalyst is nothing without the optimal operating conditions. So that is what we will look at in the second instance of this presentation, and something which we will do based on machine learning techniques. In a third short section, which is in fact 2bis section, I would say, I will then focus on interpretation techniques, because the advantage of machine learning models being that they are relatively easy to use, that they are relatively straightforward to construct. Their downside being, if you want to learn something from them, well, you need particular techniques. The model by itself will not necessarily tell you a lot. You need dedicated interpretation techniques in order to do something with the machine learning models. And of course, I will end by some conclusions and some future perspectives. So first, the catalyst screening. Finding an ideal catalyst, you can in fact say it's a kind of search for a needle in a haystack, because there are so many variables that are at your disposition to use to make different catalysts, and those catalysts can have quite different performances. So it can feel a bit like being lost in space. Now, nevertheless, I would say there are two kinds of options. Sometimes the behavior of a catalyst is quite well understood, and the influential factors are relatively easily determined. So in that case, well, you're quite lucky, and you can find the needle in a relatively straightforward or in a relatively well identified manner. If the impact of the various features is quite significant, leading to a clear optimum. Unfortunately, reality will typically be more like we have it over here. It will be a very complex search, and well, being with the head in the haystack, it becomes difficult to be sure what is now the good and ideal catalyst. Nevertheless, the challenge is to approach the catalyst design as systematically as possible, and hence in order and hence with the aim of finding the ideal catalyst in a reasonable amount of time, or in a controlled amount of time. How do we propose to proceed in that case? Well, that is to, with the fundamental model, with the elementary step-based kinetic model that we have, is to do what we call a virtual catalyst design. And that involves, of course, a screening. So the methodology is displayed in the figure here on the left, and we start in this spot with the generation of sets and combinations of descriptors in a relatively random manner. And each set of descriptors corresponds to a virtual catalyst. So in this matrix, this matrix represents n virtual catalysts, represented by the m rows, each of them having m descriptors. This set of catalyst descriptors is then pulled through the single event microkinetic model to provide us with the corresponding n conversions and the corresponding selectivities, product selectivities of the various components of interest. In order to do the virtual catalyst design, we will need to match it with the performance of real catalysts. So there is an input here of experimental data of catalysts that has been acquired. And with the simulation results, together with the simulation results, there is then a comparison of the simulated performances as compared to the experimentally observed performances. And if for all responses, if for the conversion as well as the selectivities, we have a sufficient agreement, we have a sufficient match between those simulated performances and the experimentally observed performances, we consider the virtual catalyst screening as having converged, and it means that the catalyst descriptors to understand, to match the experimental behavior have been sufficiently defined. If that match is not sufficient, we will need to generate more catalyst descriptors. Of course, we can now target the generation of the catalyst descriptors around the regions which are exhibiting the closest match between the catalyst descriptors from the previous generation and which were matching with the experimental results, in order to generate an extended set of catalyst descriptors and an extended set of virtual catalysts. So once we have sufficiently iterated and identified a set of catalyst descriptors which allows to sufficiently closely match the data, match the experimentally observed data, we can proceed with the identified descriptors. In this particular case, we went for the model as it was constructed originally by Lozano Blanco, and this gives an overview of the kinetic descriptors as they are indicated over here, and then the catalyst descriptors were the ones which are still variable. It was a base case for an iron catalyst with some potassium promotion that was originally there. So, and for that base case, we had performances simulated like this with good statistics overall. So, based on this model and with these kinetic descriptors, we now left the catalyst descriptors free to move in order to do a virtual catalyst screening. And here you see an example figure where for different catalyst descriptor combinations we had simulated values for the conversion and the light olefin selectivity at these operating conditions. So we sampled the entire catalyst space and we looked for combinations of catalyst descriptors that were matching the experimentally observed behavior as reported by Bangu et al. For iron on carbon nanotubes and for a bismuth and lead promoted variant of that catalyst. Here, the focus is on the light olefin selectivity as it was reported, but note that other product selectivities were also considered, such as the methane production, for example, the formation of heavier components, as well as the CO2 formation. So that allowed us to further identify the descriptors. So here you see the comparison for the conversion values that were obtained, And then here we have the various selectivities to methane, again, light olefins that is repeated, the C5 plus and the CO2. And these are the agreements that we were able to obtain for the three different catalysts, the benchmark iron catalyst, and then the variants promoted by bismuth and by lead. And that led to the following catalyst descriptors with this unique set of kinetic descriptors that we were having. What can be seen in these catalyst descriptors, that is that the one for hydrogen, the atomic chemisorption entropy for hydrogen, that it is not varying a lot. It takes values in a very narrow range of values, and meaning that the model simulations will be quite sensitive to the value of the atomic chemisorption entropy of hydrogen. For carbon and oxygen, that sensitivity is a bit less pronounced. And we see wider variations there. We also see how for the base iron catalyst, it is mainly the oxygen chemisorption enthalpy which is deviating from the other two, whereas for the atomic chemisorption enthalpy for carbon, it is mainly the bismuth one which is deviating from the others. Now, what is happening with the, in this case, we are taking a look at the conversion as a function of the atomic chemisorption enthalpies for hydrogen and carbon. And we take that one at the fixed oxygen atomic chemisorption enthalpy corresponding with the lead promoted catalyst. So if we traverse along this figure, along these axes, for example, we will have a kind of volcano curves. So it means that we will start from a low value, go to a maximum, and then go further again to a lower value. Taking a look at the range of the values, you can see that the atomic chemisorption enthalpy for hydrogen is much more influential than the one for carbon, which spans a range over about 100. We do see in terms of conversion, well, that's at least apparently this lead iron based catalyst for sure in the direction of the hydrogen atomic chemisorption enthalpy seems to be situated at more or less the optimal value. Note, however, that this is a conversion value. If we think of the light olefin yield, also the selectivity to those light olefins is important, of course. And that selectivity is what we have next here on the next slide. So on this figure, we have again the atomic chemisorption enthalpies of carbon and of hydrogen for a fixed chemisorption enthalpy of oxygen. And here we see if we would manage to particularly tune the hydrogen chemisorption enthalpy, that we would be able to go to a catalyst which would even have a more pronounced selectivity to light olefins. Whereas if the hydrogen chemisorption enthalpy would be stronger, would be more pronounced, then we would go to the catalyst C, which is one having a higher methane production. And that is something which can be understood indeed. If there is more hydrogen on the surface, the hydrogenating power of the catalyst will be more pronounced. So the probability that such a catalyst will not lead to heavier, to C2 and higher species, but that the monomers are further hydrogenated and lead to methane, that is something which can be understood from that high interaction, that pronounced interaction of hydrogen with the catalyst surface over here. Note, however, in terms of selectivity, the point A would be the better catalyst. But the selectivity alone, of course, is also not the only factor which plays. There is the conversion, so it is conversion and selectivity which do play together. And when we multiply conversion and selectivity, we do have the yield which we are ultimately mainly interested in. And this is then, and this has then been represented in these 3D figures. So on the previous figures, we were essentially having a kind of projection of those isosurfaces on a basal plane. But here we also allowed the oxygen chemisorption enthalpy to vary. And we indicated the surfaces of identical values of the CO conversion, the light olefin selectivity, and the yield of the light olefins, which is essentially obtained as the product of the conversion and the selectivity. And then we see that the range, the area of high yields that can be obtained, so combining high selectivity with higher possible conversions, that is situated down here. So in a range of values for the atomic chemisorption enthalpies of hydrogen, carbon, and oxygen, in the range of 234, 622, and 576 kilojoules per mole. So being able to get there would lead to a light olefin yield, or could yield to a light olefin yield of up to 50%, as compared to the presently obtained yields, which were limited to 20% for the base iron catalyst, and 27 and 30% for the bismuth and lead promoted variants. Of course, the challenge is then to identify which true catalyst would correspond to this combination of catalyst descriptor values. Fine. So far, I have been focusing on a catalyst screening, a catalyst design at a single set of operating conditions. Of course, a catalyst, a process does not have to occur at a single specific set of operating conditions. No, also those operating conditions can be a matter of optimization, because a different catalyst may and will probably typically mean also different operating conditions, different optimal operating conditions. That is something which in principle could be extended according to the same methodology as what we have used for the catalyst design. But for reasons of generality and also reasons of showing the potential of different kinds of models, more particularly for the operating conditions, we went into machine learning techniques. And why did we do so? Well, we did do so kind of recognizing that the construction of microkinetic models in terms of elementary steps and detailed reactor equations, that it is a time-consuming effort, that not necessarily every individual researcher has the capabilities nor the time to do so. And hence, thinking of a balance between effort to be spent on the modeling and insight that can be gained thanks to the modeling, one could consider to move towards machine learning, which is more based on apparent models, but which will be more suited for automated treatment of data, automated guiding of the researcher through the catalyst design and operating and optimal operating conditions selection process. So how did we do that in this case? Well, for the time being, of course, when you work with a machine learning model, you also need to train that model. And what we have done in this particular case was that the effect of the operating conditions for Fischer-Tropsch synthesis was calculated based on the single event microkinetic model as it has been discussed before. Those data were then trained with multi-response prediction for various kinds or 4 different kinds of machine learning models. And those predictions were then compared to the, well, you could say experimental or the training data that were generated using the single event microkinetic model. And in the end, the best machine learning model was also tested for its interpretability, verifying whether what we had learned with the single event microkinetic model, whether we can find that back in the machine learning model, in order to ensure that if later on we would make use of machine learning alone, no longer being supported by a fundamental kinetic model, by an elementary step-based kinetic model, that we would still reach the same conclusions. So this was the strategy that we essentially have followed. So generating data using the single event microkinetic model at different operating conditions, then trying to match those data with different types of machine learning models, linear regression, support vector regression, k-nearest neighbors regression, and artificial neural networks, to then define or identify the best machine learning model and do some interpretation with it. So for the training data generation, we made use of the model that I have discussed before, but now, of course, with the catalyst descriptors, as we have determined them in the first part of this presentation. And we have used the following range of operating conditions in order to generate the training data for the machine learning models. There are various pieces of information we could display for the training data, but the ones we have particularly focused on were the behavior of the carbon monoxide conversion. So it's effectively the conversion which is here, and the light olefin selectivity. So what these plots essentially tell us, that is that the behavior of the CO conversion and the light olefin selectivity is nonlinear in nature with respect to the temperature and the pressure. Although at lower temperatures, there is maybe a relatively constant behavior or at least linear behavior, which is mainly due to the lower conversions which are reached in this area. At higher temperatures, there are more pronounced differences in conversions, and there you see a more pronouncedly nonlinear behavior. Also for the light olefin selectivity, there is this particular range of the values at higher temperatures and lower or not so high pressures, where there is a pronounced higher light olefin selectivity, which is the interesting one to try and determine and understand better. So the various kinds of models that we have used were the lasso regression, which is essentially a model which is linear in the parameters. A second one was the k-nearest neighbors type of model, which is essentially determining the value of at a certain set of operating conditions from the k nearest neighbors that are contained in the training data set. So, and k being the number of training points that is considered. There is also the supported vector regression, which is, you could say, a kind of improvement of the lasso regression, but where certain differences, as long as they are within a certain set, or as from the moment that they get beyond a certain set, that they are counted with another weight in order to do a proper weighing of that regression, which makes it less susceptible to the impact of outliers. And then there are the artificial neural networks, which work with an input layer with hidden layers. So here there is only one hidden layer which is shown, but there can be several, and each hidden layer also contains a certain number of nodes. So the optimization, for example, of the number of layers and the number of nodes, that is something which is a matter of investigation when constructing an artificial neural network model. Something which we have done and reported on, but which I will not dwell on in this presentation. So the results that we have obtained for the CO conversion using the various techniques clearly shows how the lasso regression has difficulties in capturing the nonlinear behavior of the conversion with the operating conditions. You see, in fact, by this behavior that the lasso regression is essentially behaving or approximating the behavior linearly. And we see how KNN supported vector machine regression and artificial neural networks are, you could almost say, increasingly and certainly supported vector machine regression and artificial neural networks are best capable in reproducing the generated data. Continuing towards the light-olefin selectivity, the essentially linear behavior of the lasso regression is confirmed, making it clear that a lasso regression does not suffice to describe the pronounced linearities that are encountered that are typically encountered in chemical kinetics. K nearest neighbors, as such, is doing a better job, although the island of optimal behavior is not so accurately reproduced as it was the case with the supported vector machine regression and the artificial neural networks. So these latter two stand out as the best candidates in order to reproduce chemical kinetics data sets. And in order to compare them better, to compare them fully, we look at the root mean squared deviations, the root mean squared errors that have been obtained for the various machine learning models. And here we see how, well, in the first instance, we can look at the training data set. So we see how lasso regression has a root mean squared error both for the CO conversion as well as the light-olefin selectivity, which is an order of magnitude higher than the one obtained with supported vector machine regression and artificial neural networks. The test root mean square error for lasso regression is even significantly higher than that of the training data set. So that only confirms more pronouncedly what was visually already quite clear. Because of the way the model works, for KNN, we could not really make the distinction between a training set and a test set. But if we just look at the test set already, we can also see how the root mean squared error for the k nearest neighbors machine learning type of model is also performing significantly worse, exhibiting a higher RMSE than the supported vector regression and the artificial neural networks. That means that we're left with the comparison of the supported vector machine regression and the artificial neural networks. So you see that the RMSEs that they exhibit are relatively close to each other, or are quite close to each other. Although maybe the one for the light olefin selectivity is more pronouncedly better for the artificial neural network than for the supported vector machine regression. So you can say because of that, we do have a preference already for the artificial neural network. And that is even, that preference becomes even more pronounced because when you look at the RMSE for the test data set as compared to the training data set, we see that it gets more worse for the case of the CO conversion with the supported vector machine regression as compared to the artificial neural network. And even for the light olefin selectivity, the root mean squared error obtained for the artificial neural network is slightly below the one obtained for the training data set. So that makes us prefer the artificial neural network for the simulation of the Fischer-Tropsch synthesis kinetics according to a machine learning model. The question which remains now is how to get to an interpretation of the results of the performance of such a machine learning model, how compared to a fundamental microkinetic model, how do we need to understand what the relative importance, for example, is of different operating conditions or of different features. And that makes that we should try to open the black box. So we have a black box here, but in fact we want to try to get an insight in how that black box is operating. And understanding the behavior of that black box is something which, well, how easily that is possible also depends on the kind of black box that we are trying to open. Models that are purely linear in nature, they are in fact quite straightforward to open, to disentangle, to interpret what is happening. But the more complex models, such as the artificial neural network ones, they are typically the hardest ones to interpret, and hence we will need to rely on interpretability techniques if we want to make use of such models. And that interpretation should, for example, allow in helping the ranking of the process variables depending on their impact on the output, and also understand combined effects and correlation of different input features. That is also something that could be identified. So things that exist and are discussed in some more detail in some work that has been published by Anoop last year are related to global interpretation, and there we can look at permutation importance, which is something which mainly allows to probe the impact of an error in data handling, what impact that could have. We can take a look at a local interpretation. So what is the impact of different features at a certain set of operating conditions. That is what the SHAP method or Shapley values are probing. And then there is also the combined influence of factors with the so-called partial dependence plots. So, as I said, we have taken a look at all three of them. More information you can find in here. The one I will focus on for today, for the next few slides, will be the one on the local interpretation, making use of those SHAP values. So, what will the SHAP value do? Well, the SHAP value is, and well, I looked for the actual definition and the actual calculation of the SHAP value, and you can see it as the average expected marginal contribution of features on the performance that is being analyzed. So it's a whole definition. But it means that if you have, for example, the impact of the temperature, that the SHAP value will make a calculation of, if you look for each possible condition, well, it will determine the average expected impact of the temperature at each possible condition. The mathematics which are behind, they remain relatively straightforward for linear models, but for more complex, for any model, particularly non-linear models, they become significantly more complex, and there it needs a more stochastic approach to effectively calculate those SHAP values. So all in all, summarized, we can see those SHAP values as a kind of local linearization of the complex machine learning model. Despite its local character, SHAP values can also be employed globally, depending on how the calculation of the impact is done. And if we apply that towards the Fischer-Tropsch synthesis, we see here the relative ranking of the impacts of the various operating conditions. And so clearly pressure has most impact both on conversion and light olefin selectivity, followed by the pressure, and then followed by the space-time and the hydrogen to carbon monoxide ratio. Although for the light olefin selectivity, the ranking between the space-time and the hydrogen to CO ratio is more or less similar, so there is no significant difference in impact there. The upper figure represents the global impact. The lower figure represents the true local impact. So from the wide distribution, you can see how each of the variables, how the global the global impact behaves, so such that it is more pronounced for temperature than pressure, space-time, and hydrogen to CO ratio. And the color gives an indication whether deviations are positive as compared to the average, or whether they are negative. So, and here you can clearly see how the pressure has a positive effect on the conversion, but a negative effect on the light olefin selectivity, which indeed is logic, because at a higher pressure, the hydrogenating power will typically be more pronounced, and that will reduce the light olefin selectivity. You also see, and especially in this region and here, that the colors are not a unique figure or a unique function of the value on the x-axis, and that indeed corresponds with operating conditions, and the impact of the pressure will not necessarily be exactly the same at different operating conditions, leading to the same value or that is put on the x-axis. So that is how we can analyze the relative importance, how we can analyze the performance of a machine learning model. So to conclude, I hope to have convinced you that modeling, both by microkinetic modeling, elementary step modeling, and machine learning modeling, that it can provide crucial insights in how reactions performances relate to input and operating conditions, and that it will be a matter of balance between effort and insight that is pursued, whether one will go rather for elementary step-based modeling or for machine learning techniques. For our case study on Fischer-Tropsch synthesis, we started with a single event microkinetic approach for virtual catalyst design to identify the catalyst descriptors leading to an enhanced light olefin selectivity. And we then made use of machine learning methodologies for optimizing the operating conditions, the machine learning models that were trained based on single event microkinetic data. We found that nonlinearities in chemical kinetics, that they require artificial neural networks and supported vector machine regression in order to simulate those behaviors properly, rather than making use of lasso or KNN types of regression. And interpretation techniques such as the Shep value, they allow opening the black boxes which machine learning models essentially are. And as future perspectives, of course, the challenge is to link back, feed back what we have learned thanks to the model, feed that back towards the experiments. We're currently also looking to the number of data points required for training the machine learning models. From how many data points onwards do we get reliable machine learning models or not? And another factor that we are using machine learning for is to perform experimental design and see how with machine learning we can reduce the number of experiments to be performed. That was essentially what I wanted to convey. So, of course, I also want to acknowledge the financing instances and, of course, you for your kind attention.
Thank you, Joris, for this interesting presentation. Are there any questions for Joris?
Hello, just I have a question.
Yes, André, please go ahead.
So first, thank you very much. Very nice presentation, and so we work a lot together. My question is actually, you show nicely that microkinetics and also machine learning can explain and say predict kinetic data in terms of temperature, gas space velocity, so pressure. I just wondering whether maybe in perspective it can be considered also for optimization of chemical composition of the catalyst, to say which promoters we need to add, because it will be extremely helpful for us who are developing catalyst.
Yes, I think that would be kind of the holy grail in catalysis. But I think that's exactly the challenge, that when we have determined catalyst descriptor values, in order to relate them properly to a potential chemical composition, I think there right now we have used we have in fact focused on 3 of the catalysts that you have produced and tested. And we use those 3 points. I think we should have used, or we should use more points in order to find relationships between the catalyst composition and the descriptor values. And once we would have such kind of relationships, I think we can close the gap. I think the challenge there is, to some extent, the amount of data that is required, and the amount of data that is required for catalysts that are maybe considered as not optimal. So that makes it, I think, typically challenging to convince the experimentalist to do a bit more experiments on catalysts from which he would believe they are not really worth investigating anymore. He wants to go to a new material. But we do not necessarily have sufficient information yet to extract everything which is in the kinetics. I think that's where the I think that's where the point of convergence is situated.
Okay, yeah. So, thank you.
Any other questions for Joris? If not, to end, I would like to thank both Benoit and Joris for their interesting presentations and all of you for participating to these guest lectures. I would like to acknowledge the funding received from the European Regional Development Fund via the Interreg France-Wallonie-Vlaanderen program, together with funding from our local authorities, being the provinces of West and East Flanders, the Walloon Region, and the Walloon Public Service on Economy, Work and Research. Thank you all and have a nice afternoon.